Hi, I'm Xiangyu Wu from the High Performance Robotics Lab at UC Berkeley, and I'm going to present our work in-flight range optimization of multicopters using multivariable extremum seeking with adaptive step size today. Nowadays, multicopters have been used in a lot of applications, such as infrastructure inspection, package delivery, and taking pictures. Flight range is a major constraint for multicopter applications. The goal of this project is to adapt the flight speed and heading of multicopters to reach the longest flight distance. The proposed method may be especially useful for applications such as package delivery. The figure on the left shows the power consumption of a quadcopter flying at different speeds but the same heading in our lab. It flies a horizontal circular path with radius 1.7 meters because of space constraint. The point with the smallest slope when connected with the origin, which is 3 meters per second, represents the optimal range speed. Because the slope changes significantly when the speed changes, it's important to find the optimal flight speed. In addition, because the payload is often not axiosymmetric, the air drag of the vehicle at the same speed, but with different heading is also different, causing different power consumption. So optimizing the heading of the vehicle is also important for reaching the optimal energy efficiency. A major reason for us to use a model-free method is that the power consumption of multicopter is hard to model accurately. According to the powertrain, we need to model the electronic speed controller, the brushless motor, and the propeller to get an accurate model of the power consumption of the vehicle, which is often hard to do. Power consumption modeling is especially hard for applications such as package delivery, where the weight and size of packages can change for different deliveries, and that would have a significant influence on energy consumption. Because of these reasons, we propose an adaptive method based on extremum seeking. It is independent of power consumption model and is adaptive to unknown disturbances such as different payloads. In addition, it is computationally efficient and can be implemented in low-cost hardware and run in real time easily. In this slide, we define the heading of the vehicle which we want to optimize. In this figure, mu infinity represents the free stream velocity, and the orientation of the vehicle with respect to the free stream velocity is represented by the angle of attack alpha and the side slip beta. We are going to use the side slip angle to represent the heading of the vehicle in the rest of the presentation. The main contributions of this work are, first, the proposal of an adaptive method to optimize the flight range of multicopters. Second, the proposal of a novel extremum seeking controller with adaptive step size, which converges faster than the standard extremum seeking controller by blending ideas from the machine learning field with traditional extremum seeking control. And finally, we experimentally validated the proposed method and compared it with the standard extremum seeking controller. For the rest of the presentation, I will introduce the standard extremum seeking controller first, followed by our proposed method with adaptive step size. And I will talk about the experimental validation of the effectiveness of the proposed method. The extremum seeking controller allows to find an unknown time-varying operation point on a star which maximizes or minimizes a given planned output Q. The optimal set point is found by applying a small periodic perturbation, A sine omega dt, to the current reference point, R0 plus R hat, and by monitoring the changes of the planned output. It can be viewed as a way to approximate the gradient of the cost function and performs gradient descent to minimize the cost. The first-order Taylor series expansion of the current set point is shown in the first equation, where all R0 plus R hat represents the high-order terms. The high-pass filter would suppress a low-frequency signal Q R0 plus R hat, and its output is QHP. Then QHP is multiplied with A sine omega dt to get T, which is then passed through the low-pass filter. QLP is the low frequency component of xi and is an approximation of the gradient of the cost function. By setting k to be a negative number and integrating QLP, we perform gradient descent to find the optimal operation point of the plant R star. In this slide, we derive the cost function to be optimized. We assume that the multicopter is powered by an onboard battery, which has energy E full at the beginning of the flight and energy E empty when the voltage is too low for flight. We further assume the vehicle is moving with constant speed and side slip and is using constant electric power. The total flight distance is thus given by these two equations, and maximizing the flight distance corresponding to minimizing P over V, power over speed. Here's a block diagram of the proposed extremum peaking controller. The difference between the proposed method and the standard extremum peaking controller is the step size adapter. The other part of the block diagram is exactly the same. The idea for the step size adapter comes from the adaptive moment estimation algorithm, ADAM, which is commonly used in the stochastic optimization of cost functions in machine learning, such as training neural networks. The upper half of the diagram is related to the side slip optimization, and the lower half is related to the speed optimization. The goal of the controller is to find the optimal set point for side slip S and the optimal set point for speed RV to minimize the cost function Q. V0 is the initial set point for speed, and S0 is the initial set point for side slip. For this multivariable extremum peaking controller to work, the perturbation frequency for side slip, omega s, should be different from the perturbation frequency for speed, omega v. And to minimize the cost function, Ks and Kv should be set positive. The adapter takes in the output of the low-pass filter QLPS for side slip and QLPV for the speed, and outputs GS and GV. G is then passed to the integrator to perform gradient descent. The effective step size for gradient descent is KV/GV over LPV for the speed optimization and KS/GS over QLPS for the side slip optimization. And the step size adapter changes them by setting G, V, and GS. Instead of initializing the first and second moment to be all zeros, like in the original ADAM method, we initialize them according to the initial output of the low-pass filter, and thus avoid the bias correction process in ADAM. By taking exponential moving average, it helps to reduce the noise in the gradient estimation. And by dividing the first moment with the square root of the second moment, it outputs a small value when the gradient estimate has a large uncertainty. That is, the second moment is large and vice versa, which is good for the stability of the method. Another change is that when the square root of the second moment is less than a threshold, which means the algorithm is close to convergence, the output G will decrease to avoid large oscillations of reference speed and side slip near convergence. This diagram shows the role of the extremum peaking controller in the control of the vehicle. The inputs to the extremum peaking controller are the instant power and instant side slip speed of the vehicle. The extremum peaking controller will find the optimal flight speed and side slip and parameterize the desired path into a desired reference trajectory, which is tracked by the low-level position and attitude controller. Indoor experiments were conducted to validate the effectiveness of the proposed method. A custom-built quadcopter was used during the experiments. The vehicle weighs 660 grams, and the distance between hub to hub is 330 millimeters. Each propeller is 203 millimeters in diameter. We used two different payloads, One is a cardboard box payload weighing 120 grams, and another one is a football payload weighing 329 grams. A motion capture system was used for the state estimation, and a voltage and current measurement module was connected to the battery to measure the instantaneous power consumption. I'm going to show some videos in the experiments. In this experiment, the goal is to find the optimal range speed and side slip with a box payload. The initial conditions are 2.2 meters for speed and 50 degrees for side slip. After about 100 seconds, the proposed method converges, while the standard method has not. The standard method took 100 seconds more to converge, 50% slower than the proposed method. In another experiment, the goal is to find the optimal range speed and side slip with the football payload. Initial conditions are 1 meter per second and 25 degrees. After about 100 seconds, the proposed method converges, while the standard method has not. The standard method took 50 seconds more to converge, 33% slower than the proposed method. To verify the vehicle converges to the optimal range speed and side slip correctly, we experimentally evaluated the cost function and provided the ground truth values. Each data point in this figure is the average value of 15 seconds experimental data with a frequency of 100 Hz. For the box payload, the optimal range cost function reaches a minimum value when the speed is between 3 to 3.5 meters per second, and when the side slip is between 65 to 100 degrees. For the football payload, the optimal speed is about 3.25 meters per second, and the optimal side slip is between 70 to 95 degrees. When the box was used as a payload, the performance of the proposed and standard extremum seeking controller is compared in the left figure, in two tests with different initial conditions. In both tests, the proposed method converged in about 100 seconds, while the standard method took 150 seconds to converge in the first test and 200 seconds to converge in the second test. And when the football was used as a payload, the performance of the two methods is compared in the figure on the right. In the first test, the proposed method converged in about 75 seconds, and the standard method took about 125 seconds. And in the second test, the proposed method took about 100 seconds, and the standard method about 150 seconds. Both methods converge to values very close to the optimal values. In conclusion, an online adaptive method for finding the speed and side slip that maximize the flight range of multicopter is proposed in this work. Not dependent on any power consumption model of the vehicle, it can adapt to disturbances such as different payloads and is easy to deploy. The proposed method can mitigate the common problem of limited flight range of multicopters and thus improve their autonomy. Based on a novel multivariable extremum seeking controller with adaptive step size, it can achieve faster convergence compared to the standard extremum seeking controller. Through indoor experiments, we validated the effectiveness of the proposed method under different payloads, and it converged about 30% faster compared to the standard method. In future work, we plan to do outdoor experiments where very accurate state estimation from the motion capture system is no longer available. In addition, the vehicle can fly a circular path with a much larger radius outdoors, which reduces the effect of centripetal force or power consumption. This work was supported by the DARPA Subterranean Challenge, and the experimental testbed at the Hyperlab is the result of contributions of many people, a full list of which can be found at our website. Thank you.